Hi class, welcome to exercise 7J, graphs of hyperbolas. I just want to make a note that this is exercise 7K in the old book. Okay, so for this lesson, our examples and pre-learning will be example 23, sketching a hyperbola. And for this example, your pre-learning is questions 1 and 2 in the new book and questions 5 in the old book. And then we'll do example 24, which is intersecting with hyperbolas. And your pre-learning for this example is question 7 in the new book and question 10 in the old book. Alright, let's get on with the introduction. So to graph y equals 1 over x, let's start with a table. So the first thing I'm going to do is look at positive x values greater than 1 and the associated y with that. 1 divided by x equals 1, which is 1 over 1, which is 1. And then 1 divided by 2 is a half, 1 divided by 3, and if we stretched all the way out to 100, we would be down to 1 divided by 100. And to close that off, so therefore we can make the statement that as x heads towards positive infinity, y gets smaller and smaller. So if we look at the positive values of x that are less than 1, well, the associated y value for that is 1, of course, but 1 divided by a half is just 2. And the same will occur for 3, all the way down to 1 over 100. So that means that as x gets closer to 0, y is going to get bigger and bigger. Also, when x equals 0, that means that y equals 1 on x is the same as saying 1 on 0. And that gets dumber and dumber. So I'm going to graph the points on these axes for positive x and y, and just mark in the x and the y. So if we focus on the results we got in our table, for both tables, when x is 1, y is 1. So we had a x equals 2 and an x equals 3. And when x equaled 2, y was equal to a half. And when x equaled 3, y was equal to 1/3. And in the other table, when x was equal to a half, y was equal to 2. And when x was equal to a third, y was equal to 3. So if I'm going to draw a smooth line that joins up those dots, let's start with x greater than or equal to 1, and then x between 1 and 0. And so this here is the shape of y equals 1 on x for a positive x. Now we all know that we can't have x equals 0 because that means that we've got y equals to 1 on 0, right? But could we have y equals 0? I'm guessing you know the answer to this, but let's amuse ourselves and check. Okay, so if we've got y equals 0, that implies that there's some x where 1 divided by x equals 0. So if we multiply both sides by x, that means 1 equals 0 times x. And anything times 0 is 0, so therefore we've got 1 equals 0. No. Okay, unless you believe that 1 equals 0, obviously we can't have a y equals 0. But you might have noticed something that was occurring in the graph that we did before. And the fact that we can't have y equals 0 and we can't have x equals 0, we're going to bring back another idea that we've covered with exponential graphs, and that was asymptotes, which is when a graph gets closer and closer to a line, but never actually gets there. So you saw before that as x gets bigger and bigger, y gets smaller and smaller. And this means that as x approaches infinity, we have the asymptote y equals 0. So if I drew the line y equals 0, which hopefully you know is the x-axis, right? Y would start at 1, then at 2 we had a half, 3 we had a third, and as it got on, it would get closer and closer, but never actually touch it, despite getting closer and closer. So I think that asymptote was fairly obvious, but not so obvious is an asymptote x equals 0. So if this line here was x equals 0, which is just the y-axis, right? And if you remember, as x gets closer and closer to 0, y gets bigger and bigger. So you could see something going like this. As it's getting closer and closer, it's starting to look more and more like x equals 0. But of course it never actually touches it because we can't have x equals 0. So this is what we call a vertical asymptote. And the concept of a vertical asymptote might take a little bit more thinking than a horizontal asymptote, because there's something very natural about a horizontal asymptote. So if you need to, spend a little time thinking about that. Alright, so we've had a look at the graph for values of x that are positive, and we could see that it had the vertical and horizontal asymptote. But what about when x is negative? So it's going to be easier here if we start with a table, and I'm going to use x values counting backwards from -1. So for the associated y values, we just need to remember that 1 divided by minus x is the same as -1 divided by x. So that means that we've got 1 divided by -1 is -1, 1 divided by -2 is -1/2, and 1 divided by -3 is -1/3. And if we counted backwards all the way to -100, we'd get -1 on 100. Okay, so let's close off that table. So we can see that just like when x is headed towards positive infinity, when x heads towards negative infinity, y is going to get closer and closer to 0. The only difference is it's always negative. Alright, let's look at the second table, counting from -1 towards 0 with smaller and smaller steps. Now for the associated y values, well, 1 divided by -1 is done in the table above. And because 1 divided by 1/2 is 2, then 1 divided by -1/2 is -2, and 1 divided by -1/3 is -3. And if we kept on going smaller and smaller, you'd see that we'd get bigger and bigger numbers until we get to -1 on 100, we'd get -100. And by bigger and bigger, I mean bigger negative numbers. Alright, let's close off that table. So as x heads towards 0 for x less than 0, y is getting bigger and bigger, but bigger negative numbers. So if we were to try and graph that, which I will on these axes, and I'm going to mark in those points a little bit quicker this time, seeing we've already seen them in the other one. So -1 was related to -1. Oh, and I should probably mark in that this is the x and y axes. And the first point, so -2 is related to -1/2, and -3 is related to -1/3. So I'll mark in those points and draw that curve smoothly. Well, attempt to. Alright, and similarly, when x is -1/2 and -1/3, it's related to y is equal to 2 and 3 respectively. Well, -2 and 3. Alright, let's mark in those points and draw this curve as smoothly as possible. It's probably as good as I'm going to get. But hopefully, despite my lack of artistic skills, you can see that we've still got a horizontal asymptote here of y equals 0, as we're heading off to -infinity there. And there's a vertical asymptote of x equals 0. Well, as x gets closer and closer to 0, y heads off to -infinity there. So with our vertical asymptotes for both the positive and the negative versions of x, this is why we call this graph a rectangular hyperbola. That's the graph for y equals 1 on x. So to demonstrate that, I'm going to draw these axes, but instead of calling this the y-axis, I'm going to make a point that it is actually x equals 0. And instead of calling this the x-axis, we're going to call it y equals 0. So when I draw these, the first thing I'm going to do is mark in the point 1, 1 and -1, -1. Okay, because 1 divided by 1 is 1 and 1 divided by -1 is 1. Then we can mark in the lines where x is less than -1 and greater than +1. So here is the less than -1 and the greater than +1. You can see that these are both going towards the horizontal asymptote y equals 0. So then we can mark in the part where x is between -1 and 0. Okay, and I'll mark that in now. And then you can do the bit where x is between 0 and 1, which is this one here. And that will give us the vertical asymptote x equals 0. And the reason we say rectangular is because you can see we've got the two different asymptotes at 90 degrees to each other. So this is all limited by my drawing. So it is time for us to explore y equals any a divided by x using this GeoGebra applet. Alright, so here is the graph of y equals 1 on x, and you can clearly see the defining shape of the hyperbola with the axes being the asymptotes. I have this slider here where I can change the number that's being divided by x. So if I was to make that 2, you can see that we've got the same general shape, it's just that it's now further away from the axes. And that's highlighted by this grey dashed line here, which is 1 on x. Now if I turn on these points, the reason that it's further away becomes clearer. So you can see that when x is equal to 1, 2 divided by 1 is 2. And you can also see that when x is 2, that 2 divided by 2 is 1. So that's why we've got these 2 points here. Whereas the graph y equals 1 on x passes through the point 1, 1. Now you can see that the graph will get further away as I move to 3 and 4 and 5. And it's important that you notice the curve where x is negative. So just like we saw in OneNote, it's basically the same curve as where x is positive. It's just that it's upside down and backwards. Now as we noticed, a divided by x goes through the points x is 1 and y is a, and x is a and y is 1. And that's why it moves further away from the axes. Now let's have a look at how the opposite happens when x is small. So I'm going to start by moving a to 0.5. And sure enough, you can see that this pattern continues. In fact, the smaller a gets, the closer this curve gets to the axes. Alright, let's put that back to 1. So hopefully you're going to be able to guess what's going to happen when a is negative. So for example, if a is minus 1, when x is positive 1, y is equal to minus 1 divided by 1, which is minus 1. So let's look at that. And sure enough, we're going to see that the positive values of y that were here flip to negative values of y, which are here. And where the negative values were, they flip to where the positive values are now. So basically, we've got the same graph. The only difference is that instead of being in these two quadrants, it's in these two quadrants. And so this is a negative hyperbola. And with negative hyperbolas, basically the same things happen as the positive hyperbolas. So minus 3 on x is going to be further away from the axes, and minus 1/2 of x is going to be closer to the axes. So the key to drawing a graph of a divided by x is this hyperbola shape in these quadrants with a negative a, and these quadrants with a positive a. Also, the bigger that a is, the further the curve is away from the axis. And the other point to notice is that when x is equal to 1, y is going to equal a. So we can see it's 2.4 here, and a is 2.4. And finally, we've got to take care of the asymptotes. Hopefully you can see throughout this that the asymptotes never change. So let's zoom out to make that even more obvious. So when a is positive, we can see that this part of the curve comes closer and closer to y equals 0 on the right and x equals 0 on the top, while the other side goes towards y equals 0 on the left and x equals 0 at the bottom. And when I make a negative number, we're still heading off to the same asymptotes, just from different quadrants. Now this is why we call them rectangular asymptotes. Alright, let's go back to OneNote. On top of graphing these hyperbolas, there's one other thing we're going to be looking at, and that is the intersection of hyperbolas and lines. So we can describe a hyperbola as y equals a divided by x, and we'll describe our line as mx plus c. So that means that if the hyperbola is equal to the line, then a on x has to be equal to m times x plus c. So if I multiply both sides by x, we get a is equal to mx squared plus cx. And if I subtract both sides by a, we can now rewrite it as this. And that looks nicer if I have the 0 on the right. So we're left with mx squared plus ca minus a equals 0. So therefore, we need a quadratic solution. So the possible amount of solutions we could have are 2 solutions, which could look something like this, and 1 solution, which could look something like this, or even this. And of course, quadratics have the possibility of 0 solutions. And in this case, it could look like this. But just note that in our examples today, the line will be either y equals mx or y equals c, which are much easier problems. But I'm hoping that you will consider something a little bit more challenging like this in our challenge. Alrighty, before we get on to challenges and the other examples, you really should pause that video now and do the building understanding questions in the new book, which translates to questions 1, 2, 3, and 4 in the old book. And then we can get on to the next section. Okay, so as we saw in the introduction, if we're going to sketch the graph y equals a divided by x, then if a is positive, you will get some graph that looks a bit like this. And if a is negative, then you get a graph that looks a bit like this. Also, when a is equal to 1, then a divided by x equals a on 1, which is just a. And when x is equal to minus 1, then a on x is equal to a on minus 1, which is minus a. So that means that 1a and minus 1 minus a are on the graph. So let me mark in 1a on both of these graphs and minus 1 minus a. On top of that, when x is equal to a, then a divided by x equals a divided by a, which is 1. And when x is equal to minus a, then a divided by x is a divided by minus a, which is minus 1. So that means that a1 is also on the graph, and so is minus a minus 1. So if we go back up to the graph, I can mark those both in here. So in the first one, that's x is a and y is 1, and x is minus a and y is minus 1. And for the negative one, a will be in the negative direction, and there'll be a point a1 there, and minus a is in the positive direction, and obviously that's paired with minus 1. Alright then, let's get on with example 23, where we're going to sketch the following hyperbolas and mark in where x is equal to 1 and x is equal to minus 1. So in part A, a hyperbola is y equals 1 on x. Now this is no different to what we did before, so I'm going to quickly paste in some axes. And let's take some notes that when x is equal to 1, y is equal to 1 on 1, which is 1. So that means we have the point 1, 1 on this graph, and let's mark that in. And similarly, when x is minus 1, then y is going to equal minus 1. So the point minus 1 minus 1 is on this graph. And we should mark that in as well. Now to help me draw it, I know that this here is going to be a half and 2, and 2 and a half, 1/3 and 3, and 3 and 1/3. And similarly with minus a half 2, and minus a third 3, minus 2 and a half, and minus 3 and a third. Just for my sake, I much prefer to have those dots in to guide my curve. So let's have a go now. And the other side. That's not too bad for me, hey. Alright, I'm going to move on to part B now, where they want us to graph y equals 2 on x. So let's paste in these axes and quickly work out that when x is equal to 1, we've got y is equal to 2 on 1, which is 2. So therefore we have the point 1, 2. And similarly, we'll see that when x is equal to minus 1, we'll have the point minus 1, minus 2. I'm going to mark in the point for x is 1 and y is 2. And where x is minus 1, y is minus 2. And we know that 2 divided by minus 2 is minus 1. So that's that point there. And then 2 divided by minus 4 is minus a half. So I'm going to put another point here. And 2 divided by minus a half is minus 4. So I'll put this point here. And similarly over here, I'm going to add the same points, but the positive versions. And that should guide my curve nicely. Well, the first bit anyhow. I find that negative bit difficult. It sort of goes against the way my hand moves. I might just try it in the opposite direction. Nah, No, I still miss it. Alright, let's move on to part C, where we're going to graph y equals minus 3 divided by x. So of course we need to paste in some axes where x is equal to 1, then y is equal to minus 3 divided by 1, which is minus 3. So I've got the point 1 and minus 3. And when x is minus 1, we're going to have y is equal to minus 3 divided by minus 1, which is 3. So therefore we've got the point minus 1 and 3 on this graph as well. So I'm going to mark in 1 minus 3 and minus 1 3. And once again, to guide my curve, I'm going to put 3 minus 1 and minus 3 1. So let's see if my excuse holds up as I do the negative one. Yeah, not too bad actually. So let me just make these points stand out a bit more. Alright, so that's really all it is. You know what a positive hyperbola looks like and a negative hyperbola, and then take into account where x is 1, so you know the distance from the axes. Alright, so now it's your turn. Pause that video and try questions 1 and 2 in the new book, or question 5 in the old book. And then when you've done that, we'll get stuck into the next section. To find the intersection of a line and a hyperbola, we would first describe our hyperbola as a divided by x and the line by mx plus c, and then seek to find where the hyperbola is equal to the line. Then we know that a over x is equal to mx plus c, just using substitution. And as we saw in the introduction, we could rearrange that equation to end up with mx squared plus cx minus a equals 0. And because this is a quadratic, we'll end up having 0, 1 or 2 solutions for x values. And once you've got those x values, you sub them into either equation to find the y value of each intersection. Because of course, an intersection is a coordinate. The reason why you can use either equation is because they're both functions. But before we go on with the example, we should note that if our line was equal to just a constant c, and then when the hyperbola is equal to the line, we've then got a over x is equal to c, which when you rearrange means that x is equal to a divided by c. And if you sub that into the hyperbola, y is going to equal a divided by a over c, which is equal to c. But that's not really necessary because a line equal to a constant is just a horizontal line that's always going to have the same value, right? Now the other easy option to think about is if our line was equal to mx. In other words, an angled line but passing through the origin. So that would mean when our hyperbola is equal to our line, a over x is equal to mx. So therefore a is equal to m times x squared, and a over m is equal to x squared, and the solution will be x is equal to plus or minus the square root of a over m. And you can easily find the y value by multiplying that answer by m. Now hopefully you can see that both of these scenarios are much easier. And as you'll see in example 24, that's all we're going to ask you in this exercise so far anyhow. So let's find the coordinates of the intersections of these lines with y equals 1 over x. So part A, we've got the line y equals 3. So if we've got y equals 3 and y equals 1 over x, that means we've got 3 equals 1 over x. So we can just take the multiplicative inverse of both sides. So therefore x is equal to a third. And because of our line 3, y is going to be 3 everywhere. So therefore our coordinate is 1/3 and 3 for y. So let me paste in the graph of y equals 1 on x. And I'm going to draw y equals 3. So this must be the coordinate here, 1/3 and 3. Having done all that, I still think you should have been able to figure that out immediately. Okay, so we're just going to look for the value where y equals 3, and you know that's going to be the inverse, which is 1/3. But using that formula I had beforehand, in this case, for y equals a divided by x, a is equal to 1, and for y equal to c, c is equal to 3, and we find the solution at a divided by c, which is 1/3. But that might not be totally necessary for something as easy as 1 over x. Alright, let's have a go at part B, where our line is y equals 4x. And don't forget our hyperbola is still 1 over x. So therefore we're looking to see where 4x is equal to 1 over x. So multiplying both sides by x, we want to find 4x squared is equal to 1. And then dividing both sides by 4, we get x squared is equal to a quarter. And x has to be plus or minus the square root of a quarter. And you can take the square root of the top, which is 1, and the square root of 4 is 2. So that means that x is plus or minus a half. So when x is equal to minus a half, y is going to be equal to 4 times a half, which equals minus 2. So that's just subbing it into the linear equation. And it won't take a genius to realize that when x is equal to a half, y is going to be equal to 2. So our points of intersection are minus a half, minus 2, and a half and 2. So that's minus 2 with the minus half. Alright, let me paste in the axes with the y equals 1 on x. And if our line equals y equals 4x, I know we're going to have the points 1, 4 and minus 1, 4. So let me draw the line between these 2 points. And this must be y equals 4x. And it looks like my line's a bit off, but these points of intersection should be a half and 2. So even if it's not perfect, our declaration makes it true, right? And for the other one, we've got minus a half and minus 2. So in this case, a is equal to 1 and m's equal to 4. So that means that x equal to plus minus the square root of a on m is equal to plus minus the square root of 1 on 4, which is plus or minus a half. So once again, this little shortcut isn't completely necessary, but it's good to practice your algebra, and in some cases it will save you some time. Anyhow, right about now, you should pause that video and do question 7 in the new book or question 10 in the old book. And just like in our last lesson, I think some of you will find the intersections they give us in the lesson a little bit too easy. So I have a little challenge for you. So in this case, our hyperbola y1 is equal to minus 1 on x, and y2, our line, equals mx minus 2. And what my challenge asks you is, what is the value of m if these two functions have exactly one intercept? Alright, good luck with that pre-learning. As I said, that was question 7 in the new and question 10 in the old. And good luck with the challenge if you take it on. When you get those done, come back and we can summarize this lesson. Okay, so it's undeniable that asymptotes are important again. You've seen them with exponentials, and now you've seen them with y equals 1 over x. You really need to take note of how the hyperbola relates to them. It's going to be very important in a later lesson. Alright then, so for this lesson, a successful student will know the general equation form of a rectangular hyperbola y equals a divided by x. Know how to sketch and label the key features of a rectangular hyperbola, including the asymptotes. Be able to sketch reflections of hyperbolas. And finally, be able to find the points of intersections of a line and a hyperbola. Alright, well done everybody. Keep working hard. We'll see you in the next lesson, whether that's in a video or in the classroom. Bye.